Hello and welcome back, Earth Science. Today we're going to be talking about groundwater, or water that is trapped underground. This water can reach the surface in several different ways. Uh, how we get groundwater is usually through precipitation. And then we're going to talk about later in this chapter how humans kind of interact with and influence the levels of groundwater. So let's jump right in. All right, so groundwater is most simply water that is in the ground. So normally when we get precipitation, water falling from the sky, this becomes runoff. This runoff will try to get down to the ocean. If it for some reason gets soaked into the ground, this is water entering as groundwater and becomes this water that's stored in the ground. Some factors that affect the amount of groundwater in any certain area are things like climate, the topography, how much vegetation is around, and the land use. How is this land currently being used? All right, the first thing we're going to talk about is porosity, and this is the percent of a material's volume that is pore space, or the percent that is open and has this space in there. So in this kind of picture over here where we have this greater porosity, there's more pore space here. There's lots of room here. In this one that has these little bits inside of there, there's less pore space. There's more of the space that has been taken up. So some factors that determine the porosity are the particle shape. Are they rounded? Are they more porous? Uh, these flatter and angular shapes are going to fit together better. And are the rocks the same size? Things like very well sorted rocks, like this example up here on the top, are very, and like kind of this one too, where they're more round sided, are very porous, very well sorted. And as we get to different size of materials, these smaller materials are going to fill in these areas, fill in these gaps, and decrease the overall porosity. All right, permeability is also a kind of measure of a rock's ability for water, but this one is specifically the rate at which water or other liquids can pass through the pore spaces of rock. So permeability increases with grain size. The larger the grains, the larger the pores, the more permeable this is. Because of this, things like gravel, things like sand, this water is able to pass pretty freely through there. Things like silt, it can move through, but it's much harder for that to get through. And then in things like clays and shale, these are so fine grained that they are completely forming no pore spaces. They are impermeable. They do not have any permeability. Impermeable means no permeability at all. So this water is unable to make it through there. All right, the water table. You've probably heard of the water table. This is the level underground where all the pores in the ground are filled. In some instances, it is very close to the surface. In others, it is very, very deep. There's people that have to drill their wells down considerable distances to reach some water. Water will run downhill just like it does in rivers. It's going towards the ocean. It's going towards that base level. So it will try to work its way downhill as the best way it can, in between rock fragments, in between pores, through these permeable spaces. It will continue to move in downward until it hits an impermeable layer, this silt or clay that's kind of common in a lot of areas down around the bedrock. This is where that water will hit that, and it will no longer be able to go down, so it'll start to either pool up or flow to the side. The water table has some certain zones that we're going to talk about that kind of determine where we're at in the water table, and they certainly determine how that water is going to behave there. The first is the zone of saturation. We're starting at the bottom here. The zone of saturation is the layer between the impermeable layer on the bottom to the top of the water table. And at this point, all the pores are saturated with water. There is not any kind of air inside of this space. Above this, the area between the water table and the surface, we call the zone of aeration. And in this area, water can enter this region, uh, air can enter this region, water can flow down here. It doesn't stay up here. It doesn't stay here because it's going down to the zone of saturation, down to the water table. And this can change under certain environmental conditions, more or less rainfall, more or less usage. And we're going to talk about each of those in a future slide. All right, capillary fringe. So the area between the zone of saturation and the zone of aeration is what we call the capillary fringe. It's kind of this blue dotted line here. At this point, we're going to have this capillary action where water is going to rise as it's attracted to the surface of objects. In this case, it's going to be those dirt particles, those porous rock spaces. And it's also going to be attracted to plants as well as soil. So roots are able to utilize this capillary fringe for that water to move passively up into those roots. And over here, we see some capillary action at work as this water is being drawn up that straw higher than it was normally. All right, so the water table, we often talk about springs. An ordinary well, this is where somebody has gone down and said, okay, I'm going to dig down to the water table and I'm going to transport that water back up. Either if it was on like one of these cranks where you crank down the bucket, you grabbed your water and then you cranked it back, or with pressure and pumps now, we're able to do that. A spring is anywhere where this water table is meeting a hill or a surface or the surface at all. Usually this happens on a hillside, but it can happen elsewhere as well. And the water table, like we said, is going to change during the seasons. So some wells and some springs are going to dry up and not be usable all year. All right, continuing on this kind of graphic here, we're going to talk about these artesian wells here. This is where we have a permeable layer of rock and sediment that are going to store and carry groundwater. It's kind of here, this little confined aquifer here. If there's enough of this to support a well, we get what's called these artesian formations. And what's happening is this water is getting stuck between this impermeable layer on top and this impermeable layer on the bottom here. So this water that's coming from up here is getting trapped here, and this is going to fill up all the way up to the top before it comes out here. So we can get a lot of water in here. Because of this, and this water trying to move downhill, this creates a lot of pressure that pushes this water up these things and then to the top. Kind of like you sucking a milkshake through a straw. It's like pushing that water to the surface there. So artesian wells are going to be those that are under the pressure of this artesian formation. There's no locomotion or pumping or cranking for this guy here. This water is just naturally flowing there. We also have what's called a perched aquifer or a perched water table. This is an amount of water that is trapped above the water table. The normal water table is down here. This perched water table here is above that. And we get a spring here that's forming above the water table. These ones normally will dry out in the summer and then refill under large rainfalls. But it is above the water table, being able to hold water. That's what makes it a perched aquifer. All right, hot springs and mud pots. Groundwater being underground can get into that part of underground where it is very warm, somewhere in the 1800 to 2400 meter area. It will become heated. As things heat, they expand and they rise. So this heated water will go towards the surface. This can also happen as we get like volcanic gases are heating these waters in our geothermal areas. It makes this very acidic. This allows this water to weather rocks really quickly, both mechanically and chemically. And it forms these mud pots and mud volcanoes where we're getting this very heated mud water mixture that's being heated from deep below the surface and rising up. These are very common in the States here, in areas like Yellowstone National Park. There's a whole bunch of mud pots, very cool. If you can definitely make it over there, I definitely suggest Yellowstone to all our budding geologists. Lots of fun areas there. All right, geysers. Once again, another Yellowstone Park feature here. These are hot springs. They're intermittently shooting this hot water in steam into the air. So they're not just hot springs, they're also hot springs that erupt. They have underneath the ground here a long, irregularly shaped tube that's going way down into the ground. As this water is boiling, it gets stuck inside of these kind of twisting caverns underneath. It gets under a lot of pressure. Eventually, that pressure and that heat causes it to erupt like so. Eventually, the pressure underneath is greater than the surface area here, so it's going to pop that, get that nice geyser formation. Some of them are very cyclic, like Old Faithful. They happen every so often, very recordable, very predictable. And some happen every couple of years, every couple of days. They're less predictable. All right, fumaroles. These ones always look like a dragon to me. This is groundwater that is released as steam from fissures in the ground. We find these in Iceland, we find these in Japan, once again in Yellowstone, and other regions who use geothermal energy. This is that hot water vapor reaching the surface, escaping there. Very cool. Still think it looks like a dragon. Very cool. All right, so conserving groundwater. Groundwater is a limited resource. This is a resource that we have a hard time making more of. It's very expensive to purify water. So conserving the groundwater we have is kind of a large part of our focus. 50% of our drinking water in the United States comes from groundwater. So that's half the water we care about. Conserving this is a priority. It's something that we take very seriously and that we're very interested in. All right, next we're going to talk about water budgets. A budget that you would expect is like your house is your expected income versus expected purchases. When we talk about water budget, we're going to be talking about these income and purchases using water specifically. So this is the spending and the income of water for a region. The income is going to be things like rain or snow or river water, things like that. Spending is things that are going to be lost by use, things like runoff, lost by evapotranspiration. These are all spending, ways that we spend our groundwater. Some other kind of water budget terms here. We have recharge, which is where we're taking soil water. It's filling all the way up. Eventually it becomes saturated. The surplus water here, this extra water, surplus means extra, is going to escape as runoff. It's no longer soaking into the groundwater here. So some reason that this could happen is the rainfall is greater than normal, or maybe our storage water is already filled and we're getting in some more from like a river or a flooding event, and we don't have anywhere for this water to go, so it's going to run off and move on to the next area there. All right, so our kind of final water budget slide here. If we need more moisture than we have at rainfall, the plants are going to draw from the soil, from that zone of aeration, and using that capillary action to get water. This is called usage. When we're pulling water from the soil to use it for plants, to use it as on our wells. If this usage continues and we don't get any new rainfall, we reach what's called the deficit. And this is where we cannot get the water table to recharge fast enough because the soil water is being used up. And eventually it will be too deep for these plants to reach, and they will start to look like this. Wells can run dry in the summer, same kind of thing. This usage has exceeded the area's ability to recharge that resource. So conserving groundwater, some reasons that we're interested in this is the overuse of groundwater has some very detrimental effects. As we use this groundwater, our water table is going to drop. This can cause our wells to run dry. It's very expensive to drill new wells or go and deepen your current existing well. If you're in a coastal region and we empty out all this water, sometimes water from the ocean will fill into that, and now you'll have salt water that you'll be pouring in your well. And humans cannot drink salt water, so this is a very, very real problem. It's very dangerous to drink salt water, so not great. There's a lot of contaminants, a lot of bacteria that live in there, so definitely don't want that to happen. And then another thing that can happen with overuse is subsidence, where the removal of groundwater causes a then kind of shift in the land above it, as this land above it is no longer getting that pressure. Think of like a balloon. A water balloon is exerting pressure on all sides. If we remove that pressure from the top, now this empty space here can fill in with that land, that dirt and road and building or whatever else is on top of it. So a lot of the times this will cause damage to pipes, damage to electrical works, internet lines, and can in extreme instances cause damage to buildings. We also can pollute the groundwater. Groundwater is going to always move downward, always towards the ocean. Anything that it contacts, it will try to carry it with it. This can be pollutants like fertilizers, oils, and pesticides, and other hazardous materials. And there is no simple or inexpensive way to purify groundwater. We already kind of touched on that. So keeping the groundwater we have pure is kind of the goal there, because we're not very good at purifying it once it becomes contaminated. All right, so some groundwater and geology. There's lots of minerals in groundwater. It's carrying a lot of minerals with it. If you've ever drank off of like a well, you could probably taste like the minerals inside of it. When water evaporates to become water vapor, it leaves impurities behind. So normally when we're getting rainwater, they don't have a lot of dissolved minerals inside of them. When this water then seeps into the ground, it collects minerals. As these minerals continue to get down and get carried away, they get carried into the groundwater. Eventually, they can deposit these minerals in very cool structures such as these. We mentioned hard water. Hard water is groundwater that has a lot of dissolved ions in it from these minerals. Most commonly is calcium, and then iron and magnesium after that. This calcium, iron, and magnesium are going to react with soap and prevent it from forming suds. So in this hard water here, this soap has a very thin layer of suds, and in soft water, there's a huge layer of suds here. And our artesian water is usually harder than normal groundwater. It can travel further, and it can be warmer as it's under pressure and coming from deeper in the earth. So it can have more of these minerals in it. You can get to a level where it's too hard to drink safely. But most hard water coming out of like a well is still pretty safe to drink. All right, so we talked about deposition a little bit, but there's some other mineral deposits we can talk about. These deposits are minerals that have been left behind as this water comes up, evaporates, carries all these minerals with it, and then leaves them behind as it rejoins the atmosphere. And this example here is geyserite, which is an igneous rock. It's getting dissolved by this hot water and then expelled out of geysers. So this kind of white substance is all silica that has been deposited by this groundwater from this geyser. Very cool stuff. All right, petrified wood. These are happening when groundwater is replacing the decaying wood of trees. So these are not made of wood anymore. These are actually minerals that have been deposited inside the shell of these old wooden structures. So this happens very slowly as one tiny particle of wood is replaced by minerals at a time. But it can result in very large forests of these. Usually this happens in areas that have a lot of water in them, a lot of harder water, usually around like like volcanoes and areas like that where these trees are getting buried by sudden like volcanic eruptions or mudslides, and then those particles are replaced by minerals. Cementing. So we also get, as these minerals are getting deposited, they can form cementing. This happens in sedimentary rock. We talked about them a little bit back in chapter 6. This occurs when water is carrying this calcite or the silica. Over time, more and more of this is deposited as that water evaporates, and it forms this conglomerate rock that is an excellent form of a sedimentary rock. All right, some mineral springs, a little bit different than our geysers, a little bit different than geyserite. Mineral springs also have a very high concentration of mineral matter, and they can be formed by water passing through rock that has very easily dissolved minerals, water that has a large quantity of gases that are going to form acids. This water is very hot, so we're increasing the temperature, which increases both the chemical and the mechanical weathering. So it makes it much easier for this rock to be eroded and these minerals to be carried. This example here is travertine, which are deposits formed by minerals at mineral springs. So geyserite is at geysers and travertine is at mineral springs. All right, caverns, not caves, these are caverns. Limestone is a very common bedrock, especially around coastal areas, and it dissolves very easily compared to other rocks, especially igneous rocks like granite and quartz and all those kind of very, very strong, very, very tough Mohs hardness level rocks. This limestone is very easily dissolved by carbonic acid. As we dissolve parts of the limestone, its porosity is increased. We're able to get more of this acid-rich water in there, which dissolves more, which carries away more. And over hundreds of years, these pores become very large networks of caverns. And with these caverns, we have some very, very exciting cavern features that go with them. This is formed by dripstone, which is a calcium deposit formed from dripping water in caverns. And these can only form when the cavern is at or above the water table, because this water is going to still be moving down. It's going to move down through that cavern to the water table and then continue its kind of cycle towards the base level. So stalactites, these are hanging like icicles, and stalagmites are forming from the ground up. And when they fuse together, they're called a column. And this is a stalagmite and a stalactite growing together. In these areas that have a lot of this very easily dissolved minerals, we get what's called karst topography. These are regions that have sinkholes, these sinkhole ponds, lost rivers, and underground drainages. Sinkholes, these are depressions that form in the surface because the CO2 in the water has dissolved all the rock underneath of it. And we can get what's called lost rivers, where these rivers are disappearing in one region underground. They flow out of a cave or a cavern many, many miles away. So they're going underneath, disappearing, and then coming back out when they reach the surface level again. And with that, that is going to conclude chapter 14 on groundwater. I hope you learned a lot about what groundwater is, how it affects us, how it moves, and kind of how the cycle of groundwater is. This is kind of working on that water cycle again that you guys have heard of a couple times now, kind of looking at a different facet of that. So hope you enjoyed the video, hope you learned something, and I'll see you in the next one.